All right, so we've been talking about domain and range quite a bit, okay? But we've been looking at the graph of this. Now this is in the day 2 linear functions and parent functions, not the graph paper document, okay? All right, so one thing I want you to understand here is when you are finding domain, you're really answering a certain question about the function. You're answering the question, when is our function actually defined? Okay? When you give the domain, that's what you're answering. When is this defined? Okay? And then you have this question, what can our function actually equal? Well, to answer that question, you're finding the range. Okay? Keep that in mind, and that'll help you keep these straight, all right? The range tells us what the function can equal. What are the results? The y coordinates. Okay? When is it defined? What determines when it's defined is what the value of the independent variable, or x, is. Okay, so that's our domain. All right, so let's use what we already know about these functions, about parent functions and just math in general, to figure out domains for each of these. The ranges we'll kind of address as we look at each specific type of function later. Okay? But number 53, what's our parent function for 53?
Quadratic.
It's a quadratic, all right? So what is our domain for a quadratic? Every real number, good. So we could say here x is an element of the real numbers. Okay?
So yeah, is that how you write it out like on the test?
Yeah, you could put that. Or remember, you can, if you want to use interval notation, you could just do negative infinity to infinity.
I find that so much easier.
Okay?
Just because I can't draw that little symbol in between
The R or the E?
The little E thing?
Yeah, I cannot
Just,
draw that.
just make a C and put a line through it.
It's okay. It's easier just to draw these little infinity things.
Okay. All right, now, like I mentioned earlier, you don't always have to have f and x. Here we have h of t. So when I'm asked for the domain, what variable am I looking at?
Would be changed. So what the function is defined by t.
Okay, good. It's what could be changed. The independent variable, which in this case is t. So in this case, what can t equal?
Rational.
Good, it's rational function, so it's not allowed to equal 0. All right? And remember, by stating that t cannot equal 0, we're automatically implying that t can equal anything else.
What if they subtract like from t with your domain then change?
Well, yeah, because you would have to think, like if it were 4 over t minus 3, what's going to make our denominator 0?
3.
T cannot equal 3 then,
Okay.
would be the domain. Okay?
And if you were to add like parentheses to the quadratic and then do x minus something, it'd have to be, no, never mind, because that's a quadratic.
If it were multiplied, it would still all be all real numbers, but you'd have to think about it if it were a fraction.
Radical.
Okay, so next we have on 57, we didn't have this parent function, the cube root. The cube root of x minus 4. Okay? Well, let's think about this. What numbers can you take the cube root of?
Only positive numbers.
Okay.
Oh wait, every number. Yeah.
What? Every number?
Is that 0?
Can you take the cube root of 0?
Yeah.
I'm gonna do it right
0
now.
to 0 is 0.
It should be 0, yeah.
0 times 0 times 0 equals 0. So yeah, 0. The cube root of 0 would be 0. All right.
X is element of all real numbers.
Very good. X is any real number.
That's a radical, right?
Well, it's a cube, right?
It's a radical, but notice it has an odd index. The odd index makes it so that we can do negative numbers. If it has an even index, then you're going to get imaginary numbers if you throw negatives in there. Okay? All right, how about 59? We have 1 over x minus 3 over x plus 2.
Rational?
We have two rational functions that are being subtracted here.
X cannot equal -2 and x cannot equal 0?
What do you guys think about that?
Yeah, that's right.
I like that.
You guys agree?
Yeah.
Okay? Because if it equaled 0, then this first part of it would be undefined, and undefined minus something is undefined. All right? If it equaled -2, the second half of this would be undefined, and -1/2 minus something that's undefined is undefined. Okay? So, good. Now 61. All right, 61 here. We have y plus 2 over the square root of y minus 10. Let's think about this one for a sec. There's a couple of things going on. What are the parent function here?
It's rational and radical.
It's a rational and a radical, right?
Yeah.
We have a radical inside a rational function. Okay? So we need to consider both of those as we're determining the
But this is
domain.
It says y. It says y.
It says y.
It doesn't say x. So it's
It doesn't say x. What is our independent variable in this case, though? Y. Okay? This is why I want you guys to make sure you understand that domain is dealing with the independent variable, no matter what it's called. And range is dealing with the dependent variable. So in this case, I know it's like totally weird for us to think this way, but y is the independent variable. G, the g of y, the function, is our dependent variable. Okay? So if we were graphing this, we would actually have a y-axis and a g of y-axis. Okay? And that would be strange to think about, but it still works.
When you write it as domain, would you always have x as your domain, or
No.
you write it as y?
No, up here on 55 I use t, right?
Yeah.
So yeah, whatever the independent variable is, that's what your domain is. So what do we think here?
If we put a negative in, then it's undefined because you can't root. Oh, if you do -10 and it turns out to be a negative, then it turns undefined.
Okay.
If it's 0, then it's undefined. So it has to be greater than 10. Any number greater than 10.
What do you guys think about that?
That's correct.
Okay.
Yeah.
It's got to be at least 10 to make sure that we have at least a square root that doesn't end up imaginary, right? You can do the square root of 0. However, because it's also in the denominator, it can't equal 0. All right? Because if we plug 10 in here, we'd get 12 over the square root of 0. So that would be 12, and this would be undefined. Okay? So you're right, it does have to be y is greater than 10. Okay? And that would be our domain. Any questions? Do we understand what we're doing so far? Okay? So listen, you should be able to pick out the domain if you were given a graph or if you were given the actual function. Okay? Now, here's two terms I want to make sure that we understand. A 0 and f of 0. Okay? 0 and f of 0.
Independent.
What's the difference here?
Wait, 0's not. Oh, is that an O or is that a 0? Like f of O or f of 0?
It's f of 0.
Okay, no, 0 is your independent.
Wait, what are you saying here, Donald?
X is equal to 0.
Okay, if we're dealing with f of 0, we're saying, let me get a nicer color here. Okay, If we're doing this, we're saying that x actually equals 0. Okay? Now, what does that look like, or where is that on our graph?
Independent or on the
Y.
There we go. Good. It's our y-intercept. It's right here on the graph, the y-intercept. Okay? Okay? That's our y-intercept.
Wait, why?
Huh?
Why is it because?
Because you're going to have a point 0 something.
Oh.
It touches the y-axis.
Oh,
Okay.
Okay. That's where. Okay, that's your y. Where it is 0.
Where x is 0, yeah. All right. So that kind of begs the question. So what's a 0 then?
X-intercept.
Good. It's the x-intercept. So in this case, we actually have 2 of them on this parabola. Here's a 0, and here's a 0. Okay? And you're right, it is an x-intercept. How would we find these?
Oh, we
Plug 0
plug them in.
Plug 0 in for y. In other words, whatever that function f of x is, set the whole thing equal to 0. Okay?
So if the y-intercept is over 0, we wouldn't have them anymore.
If the y-intercept was...
F0 is higher than above the 0. Yeah.
Oh, yes. Yeah, do you guys... What Donald's saying here is, if we had something like this, where the y-intercept was above the x-axis,
And we don't have x-intercept.
very good. We don't have any x-intercepts. It's never going to hit it. So there are no zeros for that function. Very good observation. Okay. All right. Now, you know that whole thing we started the day with, looking at the parent functions? Okay. I wanted you to explore a little bit, but notice they're all listed right here. Okay? You have linear, you have the linear, and you have absolute value, you have the cubic, you have quadratic. They're not in the same order. You have the radical, the rational, and this even has a couple of the ones that we didn't do.
Exponential growth.
We have exponential, and we have logarithmic.
Where's their max?
Okay? Now, one thing I wanted to point out here, okay? And that is, you'll see here odd next to some of these. And then you'll also see even next to some others. And I wanted to define these. We're not going to make a huge deal of these this year, but I wanted you guys to be aware of what these are talking about. Even functions, well, it's when we have some symmetry. Even functions have symmetry across the x-axis, or I'm sorry, across the y-axis.
So where do you find this?
Okay? And by the way, odd functions have symmetry around the origin. Watch this real quick, okay? Symmetry around the origin. I'll just show you with one of them, okay? The cubic. All right, look at this cubic. If I take this half of it and I rotate it 180 degrees around the origin, I get exactly the same thing.
Yes.
Okay? 180 degrees. If I take the other half and I rotate it 180 degrees, I get the exact same thing. Okay?
Which page are you?